Alright, so I'm going to give problem set 5 a shot. This is the one that was not a WebAssign problem. Or sorry, it was not a WebAssign set, so you guys didn't quite get answers to this. So I'm going to see how well this works with sort of showing you the plot here from the problem and then trying to write in the answers on my little scratch pad on the right. So let's see how this works out. So this is problem 1. We're given this plot, so here's number 1. And we're asked to find 3 things. First thing is the average acceleration. So that's A sub ABG for average acceleration between 1.0 and 6.0 seconds. And that's supposed to be a question mark. Poorly written though it is. So there we go. So finding the average acceleration, this is a velocity versus time plot we're given. Finding the average acceleration is pretty easy. What we do is we take our formula for average acceleration. Average acceleration is change in velocity over change in time, and then we find change. So we have our velocity at 6.0 seconds minus our velocity at 1.0 seconds, right? Because this is our velocity at the end of this stretch of time minus our velocity at the beginning is going to give our change in velocity, and then our delta t, which is just 6.0 minus 1.0. That's our change in time in seconds. Okay, so that's easy enough. Now let's figure out what we're talking about here. What's our velocity at 6.0 seconds? Well, to figure that out, we look at our plot and we just eyeball, and we see going up this 6.0 second line that it looks like we're at about what is that, 17.0? So let me see if I can get us a decent color to use. And we're going to try something here. So actually I don't want to use blue because that's going to conflict with the blue they've chosen. So let's try this. Alright, so we're at 6.0, so I'm just going to draw a little line up there. And there we are. And I'm going to go across, and we are going to find 17.0. And there we are. That's right, 17.0. So 17 meters per second is our v at 6.0 minus, and 1.0 is the original point, or the original time, so there we are at 1.0, and there's 12.0 meters per second. So 12 meters per second. All of this over 6 minus 1 seconds, and this equals 5 meters per second over 5 seconds, which equals just 5 meters per second squared. And I guess we could put a 5.0 on if we feel like it. So there we go. 5.0 meters per second squared is our answer for part A. That's pretty easy. Let's see how much room we have. Let's see if we can do part B now. So part B wants us to find the instantaneous velocity at 4.5 seconds. So V equals what at t equals 4.5 seconds? So let's see, what's our point here? 4.5 seconds. So we're looking right about right there. Now the tricky thing to do here is what we want to do is sort of find the instantaneous velocity. So we want to try to eyeball the shortest possible section of the plot and see if we can guess what the slope is. Now this gets kind of tricky. So I'm not sure how best to approach this. So I think what I'm going to do, I don't actually have a line drawing tool through this program, unfortunately. So, but what I'm going to do is I'm just going to sort of try to eyeball and sketch it, and this is going to go horribly wrong, of course, but it's worth a shot. So it's 4.5 seconds. What I'm going to do is I'm just going to take my velocity at 4.0. Let me get a different color, and ooh, a nice disgusting green. So at 4.0, our velocity is this, right here. At 4.0, our velocity is 10 meters per second. And at 5.0, our velocity is, what does it look like there? That looks like, say, we're going to call that, I don't know, we're going to call that 13 and a half. So let's define our instantaneous velocity here. Let's just take our average velocity over that short period of time, and we're going to say our velocity is going to equal, I'm sorry, not velocity. Acceleration is going to equal change in velocity over change in time. and we're just going to take as short a thing as we can. That's really all we can do here. And so we're going to go for, looks like this is 13.5 at the end, 13.5 meters per second minus, and then at the beginning down here, looks like we had about 10 meters per second. Okay, so 10 meters per second. All of this over 5.0 seconds, right? So just drawing down from here, we can see this is 5.0. Drawing down from here, we can see this is 4.0. And here we come over to 13.5 and 10, right? We look good. 5.0 seconds minus 4.0 seconds. And then this equals, well, let me put it on a new line then, equals 3.5 meters per second over 1.0 seconds. And so this is going to equal, looks like our acceleration is going to be 3.5 meters per second squared. That's our answer for part B. Okay, that's reasonable. Part C, what is the displacement of the object from 2.5 to 9.0 seconds? Oh, good lordy. All right, so this one's actually going to be kind of hard. Well, not hard. None of this is really hard, but it's going to be a little time consuming. So from 2.5 to 9.0 seconds. So what we want to do now is we need to take some data points, or pick some points that we're going to use to draw trapezoids. So let me pick, oh gosh, I don't know, let's take orange. Yeah, this is a nice disgusting orange color. Perfect. So we want to go from 2.5, which is right here, to 9.0 seconds, which is, looks like right here. So let's draw a line all the way up. So what we want to find here, remember to find displacement from velocity, we take the area under the velocity curve. So we want this area under this thing all in here. I'm not going to fill it in yet, but it's all in this area between these two orange lines and under the blue curve. So what we have to do here, really we have no choice but to approximate it using trapezoids. And just because I don't want to take a whole lot of time doing this, because I don't want you guys to take a whole lot of time to do this by hand, I'm just going to do this in two trapezoids. So we're going to do one trapezoid like this at 7.0 seconds, from 7.0 to 9.0, and then the other trapezoid we're going to do like that. And a straight line would come a little close to this blue thing here. So it's really, this is horrible. It's more like that. Let's say that. So 2.0, so 2.5, I'm sorry, is where we're starting. So what I'm going to do here for this one, I'm just going to make a little table. And I'm going to erase and get some clean space. So this is, I have to take a new page here. So let's take, for problem 3, I'm going to make a little table here. I'm going to say that t equals 2.5 seconds, and my cat is after me again. Jeez. All right. There's 2.5 seconds. In a minute, Sydney. Velocity is 7.0 meters per second. All right. And then at t equals, my intermediate midpoint here was 7.0 seconds. It looks like my velocity there is this line here. So what is this when we come across here? That is 20.0. Okay, so at t equals 7.0 seconds, my velocity equals 20 meters per second, 20.0 meters per second. And then at time equals 9.0 seconds, my velocity, looks like my velocity is 2 squares higher, so it's going to be velocity equals 22.0 meters per second. All right, so now we're just going to apply the trapezoid rule to the two trapezoids we have. One goes from here to here, and one goes from here to here. So let's do this trapezoid first. The area of the trapezoid is going to be, and this is just our usual trapezoid rule method, is 1/2 times the left side height plus the right side height. So this is really taking the average height of the trapezoid multiplied by the base. And if we want to translate this into terms of our velocity and position and such, then delta x, which is our displacement here, is going to be 1/2 times v, let's call this v initial plus v final times delta t. So they're saying over this period of time, delta t, we go from an initial velocity of this to a final velocity of this. We average the velocities and then multiply that all by the delta t, and that gives us our displacement. So for this first one, and you can see that's the same thing as calculating the area of this space, this space and this space. So let's do our first one. Let's say delta x for the first stretch of time. So we're going to take this step down here, is 1/2 times And so the first one is 7.0 meters per second, and then the end is 20.0 meters per second. And our delta t here is, let's see, this is 2.5 seconds to start and 7.0 to end, so is 4.5 seconds. So this is going to equal 1/2 times 27 meters per second times 4.5 seconds. And we're going to pull out our trusty little Windows calculator here. Still data from the last problem. So let's see. 27 divided by 2 times 4.5 gives us, and that's going to equal 60.75. What's our units here? Well, we have, right here we have meters per second, and here we have seconds. So meters per second times seconds gives us meters for our units. And I'm just about off the edge there, but you know what I'm doing. And this is actually, this may seem a little odd to be multiplying one dimension in seconds by another dimension in meters per second and then getting meters for your area. It's kind of weird, but it makes sense. It works. So that's for this first area. We found it was 60.75 meters, and then for the second one, so now we're taking these two here and we are plugging them together, and we are going to do 1/2 times, let's see, 20 meters per second, 20.0 meters per second plus 22.0 meters per second, and the time interval here is 2.0 seconds. And this is going to work out much more neatly because it's all even numbers. So it's going to equal, so basically this part where we're taking the average 20 and 22. So this is 21, I'll feed you in a second, Sydney, 21 meters per second, and this is 2 seconds. And so you multiply these together and you get 42, and well, you know, I don't know, it was 2.0, but you know, sig figs, 42.0 meters for our second bit. So you add them together, delta x total, I'm just going to put a little total subscript on this, is going to be this plus this, and the answer is going to be 102.8 meters is our approximate displacement there for part C. So your numbers might vary a little depending on how you broke it up. If you did just one trapezoid, you'll probably be a little inaccurate. If you did more trapezoids, you might be even more accurate than I am. But your final answer should be somewhere around 102.8. It won't vary by much, might be by a few squares or so. So that's our solution to part 1, and I'm going to stop right now and feed Sydney because she's drinking my water, and I will come back and hopefully finish the rest of it for you.